Ladies and gentlemen, you read his bio. You know who he is. We will be listening to him. And remember, post your questions during his talk and after his talk so we can come up with some questions to him. But for now, please listen to Max Welling.
Well, thank you, JJ. That's certainly the most festive conference I've been in for a while. Uh, so I'm going to be slightly more serious, but I'll talk with the same characteristic Dutch accent as JJ was talking. So apologies for that. I'm going to talk about pushing the boundaries of AI research as we do that at Qualcomm Technologies. Okay, so let's think a little bit about what is AI? What are the three stages of AI? So we first have perception, which is basically sensors picking up signals from the world and doing a first quick analysis, like detecting objects, recognizing speech, and more of these things. Now, at the next level, this information that has been gathered needs to be used to then reason about. For instance, once we know the objects that are in the environment, we would like to understand the scene that we are actually in. Once we have recognized the words in speech, we now actually like to understand what is being said or what is the meaning of what is being said. And then finally, after reasoning comes action. So now we have drawn our conclusions about the world, and we would like to act in the world. Like, do I overtake the car in front of me? And how do I do that? By moving the steering wheel and pushing the gas. And typically, the technology that we use for that is called reinforcement learning. Now, at Qualcomm, we focus on three pillars of AI. The first one is power efficiency. So since Qualcomm builds chips that are in your phone or in cars or in IoT devices, it's important that these run efficiently in terms of their energy usage. For instance, if you want a very large deep neural network on your phone will get very hot very soon and your battery will drain very quickly. So we look at model design, sort of designing models that are very energy efficient. We will compress existing models. We will quantize the models so that they run low precision. We will design efficient algorithms, hardware, and software. The second pillar is personalization, because since we are having sort of a model that runs on a mobile device, the data is collected on that mobile device. We would like to sort of make the so there's some sound in the background. Can that be diminished? There's some talking in the background. Yes, thank you. That's helpful. So so in terms of personalization, so since we have the data that's being collected on the phone, there is an opportunity to actually personalize the machine learning application, to the person who is using the phone by training and retraining on the phone itself, or perhaps on the car. So for that, we want to continuously be able to learn as data streams in. We want the device to be contextually aware of in which situation is it, who is using it, what is the user, is the user moving fast or slow, etc. The device may have to be always on in the sense that it needs to wait for the user to say something to it. We'd like this machine learning to be privacy preserving. Since the data is collected on a phone, we don't need to share it on a central cloud. And if we share something with a central cloud, we like to make sure that that information is properly encrypted or, in other ways protected against privacy violation. And the last thing is we would like to do distributed learning, which is we may want to train one big model distributed over many devices. And the last thing is data efficient learning. So often we don't have a huge amount of data to actually train our models from. Still, we want our models to be robust, performing robustly, even though we haven't trained them on a lot of data. And for that, we want to use unsupervised learning, about which I will tell a little bit more. and on-device training. Now, there's the typical sort of infrastructure on which these AI devices are being trained and being run is on the right. So there's the cloud, where there's a lot of data and there's a lot of training of models happening. More and more increasingly, we also have the edge clouds, which are smaller servers which are sitting, let's say, in base stations and other places. And these edge clouds are connected with 5G connections to the devices like automotive, IoT devices, and mobile devices. So at Qualcomm, we do a lot of research in a huge sort of spectrum of topics, from rather applied research, like how do you render graphics using deep learning, or how do you recognize things in video, how do you sort of recognize what's being said in a sort of phone. We can recognize fingerprints from people so they can get access to their phone. Source compression and AI for radar is that I will talk a little bit about. And as we move to the left, things get more and more sort of fundamental. So I'm going to talk a little bit about neural network quantization and AI for wireless applications, all the way to Bayesian distributed learning, Bayesian combinatorial optimization, and in the end, I also say a few words about quantum AI, which is, of course, extremely blue sky research at this point. So, okay, let me talk a little bit more about this quantization. So, as I joined Qualcomm a while ago, what I started to notice is something that I didn't really realize before. Before, I just thought of a computer as a black box at which you throw some computation, you get an answer out, basically at infinite precision. But the point is, of course, that you don't always get the precision that you may want. And there is a very clear trade-off between how much energy you use to do the computation, how much memory you use to do the computation, and the precision that you can get out of the computation. And more machine learning and sort of compute are going to integrate with each other. Machine learning is helping computation to become better and faster, and hardware will also be able to run more better and more dedicated like AI workloads. There's now chips that are dedicated to just run convolutions, which you need in convolutional neural networks very efficiently. So, but if you want to compile a neural network on a mobile device, it is really not necessary and actually not very beneficial to do all your computations at 32-bit floating point precision. So here you can see like all the zeros and ones that you need for 32 floating point precision. But very often when we train these neural networks, we actually add noise by ourselves because we want them to generalize well. This is often called dropout. And then dropout, you just kill a bunch of these neurons sort of randomly so that these neurons get noised up a little bit, and then the network starts to perform better. But it's a bit silly to at one time do computations at very high precision and then add noise to these computations. So it's much better to already do the computations at much lower precision, and then make sure that the accuracy of the neural network is still very good. And that sometimes requires training these neural networks such that that you know that it's this precision at which they get executed. So what we have done is we have built a whole bunch of algorithms that, first of all, compress the neural network to something smaller, but still maintain accuracy, but also quantize so that the computations that are being performed inside this neural network are done at lower precision. And you can get 4 times increase in performance per watt at very low cost in terms of your accuracy. And so basically, Qualcomm is betting on a future where instead of using 32 floating point computations for neural networks, we can go all the way down to 8-bit integer computations and even lower. But at this point, the hardware that's being built is mostly it has accelerators that can handle 8-bit integer extremely fast. And we have developed a number of methods, and I will zoom in on these methods that can do automated, data-free sort of quantization. You don't need to do anything except for run it through that code. And then there's more sophisticated methods which actually retrain the method so to further reduce the precision and at no loss of accuracy. So here's a couple of methods that we used. So the first one is called data-free quantization. It's basically you sort of move the ranges, you change the ranges of the weights in such a way that you actually don't even change the output of the neural network. By, let's say, if the range is huge in the first layer, you can squeeze it down and move some of that range to the next layer. And so these kind of methods are very easy to run. They require no training. They're data free. Still, if you run them, you can get 4 times increase in performance per watt, but at a loss of only 0.5% accuracy. Now, at the next level, you can say, well, let's think very hard about rounding. So if you train in high precision and then you want to compile it to a lower precision network, so that you can inference it, you can run it at a much lower precision, you can think about rounding. And the first thing that comes to mind is to round to the nearest integer. But that's not optimal, actually. It's much better to round in a very intelligent way. And you can actually learn to round. So you can sort of make sure that the rounding is optimal. And if you do that, then you can get 8 times performance increase per watt at losing 2.5% accuracy. And the last and sort of most sophisticated version that also requires you to retrain the neural network with sort of labeled data, basically we call this Bayesian bits. It sort of puts probability distributions on whether a bit is required, yes or no, and then you train basically bits to either be present or go away. So the higher order bits, the more precise bits, they might just learn to remove themselves from the computation. And this can go all the way to 0 bits. And of course, if you're at 0 bits, you're not doing any computation, and then you're actually pruning parts of the network away. And if you do something like that, which is of course, more, it takes more effort, and you have to have training data to do that. You get 8%, 8 times improvement in terms of watt, performance per watt, and only losing 0.8% in terms of accuracy. So we've actually open sourced this tool. So if you're interested in sort of working on a problem like that, I invite you to look here at this particular link here. There's an open source GitHub project where all of these compression and quantization algorithms are open sourced, and you can try them out, and you can not only compress your neural network, but you can also compile it down to something that would run, let's say, on your phone or in a car. So this tool is developed by software professionals. It's very high grade computer software. There's also benchmarks and tests in this package. It says supports both TensorFlow and PyTorch, and it's basically state-of-the-art results in these methods. Okay, so the next topic I want to talk about is has a lot to do with energy efficiency. So we are moving increasingly from images, which is still images, to video. And of course, video takes a lot more bandwidth to transfer, but it also takes a lot more compute in order to analyze, right? So to give you a few examples, of course, in self-driving cars, we have cameras that analyze the surroundings. In AR and XR applications, of course, we also have things that we need to render in front of the glass. For the AR application, we have surveillance cameras where cameras are overlooking sort of a large area and looking for things that they want to detect, like burglars or crime or something like that. And then finally, there's of course our cell phones, where we use nowadays a lot to record video. And I just want to point out that, of course, even inside an image, there is a lot of redundancy. So if we encode images, we don't encode every pixel. We use this redundancy to make a much more efficient code in order to store this image. But over time, it's even more redundancy, right? Because the next frame in a video looks a lot like the previous frame. In fact, you can almost predict what's happening in the next frame. So to analyze each frame independently, especially, to analyze each frame independently would really mean that you're doing a lot of work and you're using a lot of energy that you really shouldn't be using. So here you see a deep neural net that's analyzing this input scene, and here you see all the activations mapped deep inside this neural network. And except for this one, perhaps the top one, the other ones are really not changing very much, right? And so you should be able to use that kind of redundancy in these frames in these deeper layers in order to do the processing a lot more efficient. So let me then ask you the following question. You've looked at these 4 application areas. I'll put them back on. So out of these 4 application areas, which one do you think has the highest potential to reduce energy consumption through smart processing? Right. So here are the 4 application areas: automotive, AR, surveillance, and sort of cell phone. So which of these do you think we can sort of reduce the energy consumption the most?
And I'm asking you all to go to the chat screen on the conference webpage and type in which of the 4 areas you think bring the best results. So go to, and I will give you some time because by now we've learned that we are 30 seconds ahead of you in broadcasting, and the answers come into the website a bit slow. So no panic here, because I noticed later on that some answers to my previous question came in. Thank you so much for that. And now I'm waiting for the answers to the question, which of the video. Alex is in with his idea that probably video will give the best result and the best progress. Any other thoughts, ladies and gentlemen? We have Alex in, and I would really love to see some more ideas on which of the 4 areas will bring best results and progress. We have the video, we have the surveillance, we have the mobile phones, and which was the fourth one, Max? Help me remember.
AR and
AR, yes,
and
thank you.
automotive.
AR, automotive, yes. So we have AR, we have automotive, we have surveillance, and we have
Video, cell phone video.
Cell phone. Yes, Jana thinks video on the cell phone. Imdad thinks surveillance. There is more room for loss of accuracy. So there is more potential, he says. Ilya says the cell phones. Pranav says surveillance. So far we have two times video, we have some surveillance, and we have some cell phones. Maybe you could go, because Imdad added an argument, surveillance, because there is more room for a loss of accuracy. So there's more potential.
Yeah, so I think I agree with the surveillance, and the reason that I agree with this is that a surveillance camera is hanging still, and basically 99% of the time nothing is changing in the picture that it takes. So if you look at this one, right, there might be very little things, and certainly at night, nothing is changing. So in some sense, you're analyzing the same image again and again and again. So it's only when, if you build a neural network that only actually processes those locations in the image or in the video where things change, then you can actually have a huge amount of win in terms of energy. All right, so thanks for the answers. So now I'm going to tell you a little bit about how you can use what type of tricks you can use inside a neural network in order to compress. So one algorithm that we developed is what we call conditional compute, or gated neural networks. And the way that works is you think about it this way. So if you train a neural network to recognize cars and dogs, right, then one part of the neural network might actually specialize in things about dogs, and another part of the neural network might specialize about things about cars. Now, if I give you an image of a car, then you can just basically skip all the computation that has to do with dogs. And so how can we know this? Well, of course it's input dependent. And so before we do an expensive convolution inside a neural network, we first send an information to a gate. And the gate is basically a summary of things that happened before. The gate then decides which of the channels are going to be convolved and computed, and only those channels you compute, and the rest of the computation you skip. Right? So you're placing these gates everywhere. You're learning these gates to turn on and off for the correct computation, and then you can save a lot of energy that way. And so in this graph on the right, you can actually see the stars are the classical neural networks. So here's a classical neural network, ResNet 18. And so for this amount of compute, if you use the gates, you can increase the accuracy for the same amount of compute from 0.6 0.9 to 0.73 percent accuracy. Okay, so and now I'm going to combine this with another technology. So the technology is unsupervised learning or generative models. So there's sort of 4 different classes of generative models. One is the variational autoencoder. One is the generative adversarial network. We have the autoregressive networks, and we have flows, which is basically invertible transformations. So basically what they do is they extract features from the environment in a completely unsupervised way, and these features represent abstract representations of the world around us. And then from these representations, we can do all sorts of things. We can use them to compress. We can use them to generate, new images. We can use them to build a classifier on top of it, right? And there's a broad set of applications such as speech and video compression, text to speech or speech generation, graphics rendering where you actually generate 3D scenes, computational photography where you want to beautify an image, and voice UI. So now one particular model that we are using a lot is called the variational autoencoder. This was the one that somebody called the paper that was called out by Alex, I believe. So this model takes as input, let's say, data such as images or speech, and then there's an encoding neural network that maps it to these abstract latent variables, and then there is a decoding network that then tries to reconstruct the input, right? But it goes through this sort of bottleneck, and this bottleneck now represents abstract features of the world. So that's the autoencoder. Now, how are we using this, for instance, for video compression? So now it gets very interesting. So in terms of video compression, so there's the first frame, let's say, and we use an autoencoder. So here's an encoder module, then here's an entropy encoding. So we get sort of our latent variables. They are discrete latent variables. They go through this entropy encoding, and then they turn into bits. The bits are being sent over the channel. Now it's highly compressed and lossy compressed, actually. And then there's an entropy decoding, and then sent through the decoder from the variation autoencoder. And then we re-render the image. It's not perfect, perhaps, but it's a re-rendering of the image, but only from these bits which were being sent. And then that's the I frame. Then there's the P frame, which are basically predicted frames. So here what we do is we're not going to encode the entire image, but we're only going to encode differences, right? So in this case, we have the original image, or we have the predicted original image. We have the image at the second frame as the input. And now, basically, we do an emotion estimation module, which is what is the difference between these two frames. Those go into an encoder, and now we only encode the bits that encode the difference between the two frames, which is a lot cheaper. So this is what I talked about recently, that you should really only look at things which are changing. These are being sent, and at the output, we have a predictor for how the image is changing, which is called the warp. And then there is the error we are still making, which is the residual. These are being added up to then produce the new frame. And we sort of keep this doing for n frames, and then we go back to sort of an I frame that does, again, sort of encode the whole image. So with this kind of idea that we can use deep learning to compress video, and we can get state-of-the-art results in terms of video compression. Okay, so then a new topic, I can sort of skip this, but an interesting topic to think about is how can we use AI to solve complicated problem in wireless? So wireless is the 5G technology that is used to communicate between phones and base stations, and between phones and other phones, right? And there's a lot of really interesting problems there that can be tackled with machine learning. So let me just talk to you about one of these problems. So here's a problem that is trying to locate a user somewhere in a factory. So we have a factory, somebody's walking around in this factory. We don't use GPS, but we have some kind of transmitter that transmits RF signals, radio frequency signals, right? And we want to have centimeter accurate precision. Okay, so we know that these signals, they bounce off of all these objects, or they diffract through objects, or they scatter off of objects, right? And so it becomes a very complicated sort of soup of all of these signals which reach the receiver. So then the question really is, how are we going to use the knowledge of wireless and how wireless sort of signals propagate through the environment in order to locate the user, only using a single transmitter in this case. So here's the model that we use. So first, a little bit of a setup. So we have our transmitter, we have our receiver, and we have sort of a direct line of sight sort of signal. But because there is a wall, there's also a bounds here. So we can introduce a virtual transmitter that looks, the phone thinks that sort of that there's a virtual transmitter here that also sends a signal. Now, if we have a couple of these sort of virtual transmitters, we can sort of start to do triangulation. So that's the trick. And the trick sort of worked out in sort of neural network is as follows. So we have our sort of wireless signal, which is the channel state information. It goes into a neural network. The neural network tries to predict the location of the user. And then that's the encoder. And then the decoder says, okay, I know the location of the transmitter. I also have, I'm going to try to learn a bunch of these virtual transmitters. And then I'm going to, once I have all this information, all these locations, I can actually use a conventional physical model for the channel of how signals are being propagated to reconstruct the signal, the channel state information that I'm receiving at the user side. So since this is all fixed in a physical model, this is going to learn to predict the receiver, sort of the user correctly in order to reconstruct the channel state information. Now, this general framework is what we call neural augmentation, which are hybrid systems between sort of classical physical or signal processing models and deep learning. And we can get very good results with this. So here's, for instance, a sort of a localization example where, here are all sorts of users that we try to locate, and this is sort of the result, which is very accurate. Okay, so I'm not sure how I'm doing on time. I think I'm going a little too slow, but here's a question. Can you think of other application areas of wireless radio frequency sensing? So imagine, let's say in your home, you have a transmitter, the transmitter, or a couple of transmitters, they all send, radio frequency signals out. And what could you potentially do with that as a sort of an application area to sell, let's say?
Yes, please post your ideas in the chat box again. 2 other applications, and if it's only one, I will be very happy with that too. But together we can come to at least 2 application areas of wireless RF sensing. And while people are thinking about this and posting their answers to this question, I will tell you, Max, that if you could finish in a maximum of 5 minutes after this question, that would be brilliant, because you were asking about your time. Yes, I'm seeing if there's anything coming into the question on the application areas for RF sensing. Not yet, but as we know by now, it takes some time for people to receive our signal and for their answers to come back to the platform. So, waiting to see if there's any applications coming in. Yes, Stanislav says home robot localization and control. Imdad says emergency response optimization in location of people in case of fire. Kingsley says for farming, monitoring birds. Isabella says multi-store car park. So we have a few options here.
Excellent. Yeah, these are all great.
5.
Yeah, that's all great. I had a few myself too. For instance, you could think about making a sensor that detects whether some senior in a senior house somebody is falling. You can even go as far as gesture recognition, whether somebody's breathing. There's all these kinds of burglar detection if somebody's entering your home when you're on vacation. Sort of all of these things can be done with this sort of technology. Okay, so then for the last 5 minutes, so I'll end 6:15 then. So there's one more topic, 2 more topics I want to talk about. So this one is about AI radar. So typically, we all know radar, right? So it's a signal that's being sent out and then sort of reflects off objects and then comes back. And typically, it's very affordable. It's quite cheap to buy a radar. It's not all that expensive. It's very responsive. It can measure long range, it can measure distance, it can measure velocity, um, and it can also look through the mist, right? Unlike a sort of a normal camera. And what's happened is that so when we were switching from sort of traditional signal processing methods to deep learning on the raw radar data, we found that basically all of the the applications we could improve significantly by using deep learning on this, right? And it's also a very interesting topic for sensor fusion because you have a camera, but you also have a lidar, and you also have a radar, and all of these three signals, they need to be combined. They all have their own strengths, and they need to be combined to build a picture of your environment and to understand the scene around you. So let me go to this example here. So this is a radar, just you see the camera, but this on the left hand side is just an analysis of the radar signal, and you see the sort of the green boxes as they overlay on the red boxes. So it basically figures out precisely where the car is, and it can also figure out what the velocity of the car is relative to the car that's that you're sitting in, with quite high precision and quite complex scenes, and also quite far away. Okay, then the last topic I want to talk about quickly is completely blue sky research, but I'm completely fascinated by this, which is quantum mechanics and applying that to machine learning. So how is a quantum bit different from a normal bit? Well, a normal bit is either 0 or 1. Now, I've talked about Bayesian bits, and that's basically a probability distribution whether a bit is 0 or 1. And then a quantum bit, every bit is basically a point on a sphere, or actually even inside a sphere. So that's a much richer sort of object. And moreover, 2 bits can actually be in superposition, which means that a bit doesn't have to be just 0 or 1. It can be 0 and 1, which means that you can both be 0 and 1, which means you're somewhere on the sphere. But also 2 bits can be in superposition, or what we call entangled, so that they are somehow connected with each other. That if you know something about this guy, then you instantaneously also know something about the other bit. So that's quite mysterious, but it is the fundamental representation of the world, which is very fascinating. And of course, we can make that come out in a quantum computer. Now, what can you use something like that for? Well, there's these algorithms which can do combinatorial optimization a lot better than classical search algorithms. So there is this quantum annealing that you can, for instance, use for physical design of chips. And then there's also this thing where we can try to use this new fundamental representation to design completely new neural networks by using this entangling between these qubits, right? So now the neurons in the neural network are represented as qubits, and they are now entangled in this mysterious way. So the model that we have built is the first model that can actually run on real data. Basically, we set out to take a classical neural net and implement it in a quantum computer and see how we can do that. So the mathematics, it's basically a bunch of these quantum gates. You probably don't understand precisely how this works, but that's okay. It basically means that we have a classical algorithm that we can now run on a quantum computer. But the nice thing is that we can now, once we have this, we can slightly deform it into the quantum regime and study superpositions. So we stay close to a classical neural net, but we slightly perturb them into the quantum domain and see if we can improve sort of the performance of these neural networks, which seems to be the case, but it's still the jury is still a little bit out there. So then, in order to sort of finish off here, at Qualcomm, we are very much interested in power efficient AI because we want to run AI on devices. We conduct leading research across a large spectrum of topics, as you've seen in some of the first slides. And also, we are creating actually a platform using hardware and software so that people can actually run these AI workloads efficiently on mobile devices. So thank you very much. That was the talk. I'll open it up for discussion now.
Yes, and thank you, Max, for your talk. And we will turn to the questions. So let's see what came in. Kingsley comes up with something that he starts with quick question and then a rather long question, but I will read it out to you, Max. The quick question of Kingsley is, in terms of conditional computation, using gated networks, which parameters does the gates receive to make a decision on which parts to focus on? How do
Yeah.
you ensure the accuracy of the gate since it will serve as the first point of failure?
So the last thing was, how do you determine?
How do you ensure the accuracy of the gate since
Yeah.
it will serve as the first point of failure?
Okay. So I think it's a very good question. So there's again a bit of an echo on the line now. Um, but okay, so it's about this slide here. So it basically, so what happens is that the gate is, you can think of it as basically a part of the neural net. It's sort of a non-linearity in a sense. So you can think of it as what it does is it determines whether to do a residual step, which a residual step is basically to skip the convolution and just move the signal to the next sort of layer. But instead of actually moving it to the next layer, we will sort of first reason a little bit about it. We basically train with its parameters. So it takes the parameters from the previous convolution, right? So here is the set of feature maps from the previous layer, channel C, and then height and width for the feature maps. Now we first map that to something much smaller dimensional. So we basically average over the spatial dimensions of the feature map, and so we get one number per channel. And then that goes into a very small NLP neural network to then decide which one of these convolutions to perform. So the black ones we shut off, and the white ones we will keep. And then we're performing them, and then we move to the next level. So it is sort of a sophisticated, adaptive way of doing residual networks, maybe. Yeah, and failure, I don't know. Since it is part of the neural network itself. I don't think it's first point of failure. It's just basically, a sort of an enriched neural network structure.
Okay, thank you. Then just let me tell you that Hassan says very interesting topics. Thank you very much. So this compliment is now handed over to you. And then there's two more questions from Imdad. I will start with the first one and then see if there's time for the second. Imdad says, would quantization running at different depth levels of a, and now I have to scroll because new questions are coming in. Let me start over. Would quantization running at different depth levels of a deep network make difference, and how much? He is referring to the propagation error.
So it makes a difference in the sense that, of course, you lose a little bit of accuracy, right? But the point is that you're training these networks to lose as little accuracy as possible. And so what typically happens is that in the first layers and then the last layers, you need a lot of precision. And then in the middle layers, apparently, you don't need as much precision. But the neural network will sort of figure out itself how it can sort of squeeze out as much precision as possible, to maintain its accuracy. So there is, in some sense, perhaps propagation of errors. I mean, surely, there is always propagation of errors in these neural networks. But the neural networks gets trained in some sense to avoid this kind of propagation of errors. So I guess you want sort of more, I guess you want some kind of averaging out of these errors rather than sort of piling up of these errors, and it can learn to do that.
Thank you. I will go to a question, maybe final question, by Levente, who says, are the videos encoded by DNNs usable in safety critical applications? Is the loss of error of the encoding sufficient for applications of automobile industry, for example?
So are we talking about just about this sort of compressed video? Because there's two things, right? One is actually sort of processing the video using sort of a more power efficient algorithm. And again, whatever sort of quality metrics that we use for the original neural network, we are also going to use for the compressed neural network, right? So it's exactly the same. And in this case, also, we can very precisely control the amount of error that we have, right? Because as the error, if we want a certain precision, then we will have to send more bits here in this sort of a central layer. Um, so my answer is that yes, whenever you're happy using a neural network in a sort of safety sort of critical application, then you can also use these kind of compressed neural networks. That's not a problem. But you could argue that using neural networks in general in safety critical applications might not be a good idea unless you have very good sort of uncertainty estimation, and perhaps explainability so that you can sort of know what's going wrong. And it's a huge area because certifying neural networks is actually not very easy, but we will have to deal with in the future.
Okay, thank you. Of course, ladies and gentlemen, we will be going to one more question for the fastest finger first competition. But first of all, I will do what you cannot all do together. I will applaud Max. Thank you very much, Max, for your talk, and
Thank you.
hope to see you somewhere live. Thank you, Max.
Thank you very much, too. Bye bye.